Now we're going to talk about inverse trigonometric functions. For one thing, because they are useful when you're dealing with trigonometric problems. For another, because they're going to provide us with antiderivatives for important functions, and they're going to be tools for all the integration techniques that we're going to see later on. So let's start with the inverse of the sine function. Now we have seen that a function has an inverse function when it is 1 to 1. To start with, we have a problem considering the inverse sine function, because if you look at the graph of the sine function, evidently it's not 1 to 1. If you consider the horizontal line test, so take an horizontal line and try to see if the intersection with the graph is at most 1 point, you see that for any value in the range from -1 to 1 of the sine function, an horizontal line actually intersects the graph of the sine function infinitely many times. So it fails to be 1 to 1 in the most dramatic way. However, we could consider a restriction. For instance, so as you can see, the function is not 1 to 1, but if I take its restriction to the interval -π/2 π/2, for instance, then on that branch of the graph, the function is increasing. In particular, it's monotone and therefore 1 to 1. So the restriction of the sine function to the closed interval from -π/2 to π/2 is 1 to 1, and we could consider its inverse function. Of course, you could say that I could pick another branch where the function is 1 to 1, this one or that one, but as a convention, when we're talking about the inverse sine function, we're actually talking about the inverse of the restriction of the sine function to the interval -π/2 π/2. Picking that interval rather than another one on which the sine function is 1 to 1 is a little bit arbitrary, but as a convention, this is the one that we're going to pick, the one centered at the origin. So, the inverse sine function that we will call arcsine of course, as domain the range of the sine function, in other words, the interval from -1 to 1, and as range the domain of our restriction, in other words, -π/2 to π/2, and it's defined the way an inverse function is defined. In other words, y is arcsine of x if sine of y is x, and because we are looking at the restriction to -π/2 π/2, for the sine function, and y is between these two values, -π/2 and π/2. So this is a definition. And one remark on notations, in several books you will find, instead of arcsine, sine to the -1 to denote the inverse sine function. And this notation is in conflict with the standard convention that you use for trigonometric function. For instance, when you have sine square x with the exponent 2 right next to the function, this is a standard convention to denote sine of x that you square. In other words, it's not the function sine that is squared. It's you plug x inside the sine function, then you square the number that you obtain. So to be coherent with this use the cross support convention, when we write sine to the -1 x with the -1 next to the function, it should mean, if we were consistent, that it's a number sine of x to the -1, and when you have a number to the -1, it's just a reciprocal. In other words, it's a multiplicative inverse. But the sine to the -1 as an alternative notation for arcsine is the inverse for composition of functions. It has nothing to do with the reciprocal of sine x. So, because of that, I will not use this notation and keep arcsine for the inverse sine function. Now, what about the graph of the inverse sine function of arcsine? Here we have the graph of the restriction of sine x to the interval -π/2 π/2. And we have seen, when we were talking about inverse functions, how to obtain the graph of the inverse function of a 1-to-1 function from the original graph. What we do is look at the line y = x and take the reflection of the graph about this line. So in this case, we get the graph of arcsine, the red graph, as the reflection about y equal x of the graph of the restriction of sine to negative pi over 2 pi over 2. As a result, of course, it has domain negative 1, 1 and range negative pi over 2 to pi over 2. To see it clearer, we're going to clean up the graph. So this is what we get. This is what it looks like, and this is a picture that you should remember. One observation that you may make is because sine x is an odd function, in other words, sine of negative x is negative sine x, it goes through the origin. So when we take this reflection about y equal x, this property is going to be preserved. In other words, the fact that the origin is a center of symmetry for the graph of the restriction of sine to negative pi over 2 pi over 2, this property is preserved by reflection about y equal x. So the origin is again a center of symmetry for the graph of arcsine, which means arcsine is an odd function as well. In other words, if I plug negative x into arcsine, I get negative arcsine of x. Okay, so now what about the derivative of arcsine? Why is arcsine x if sine y is x? So we're going to start from that, right? Let y equal to arcsine x and then try to find the derivative of y. Since sine y is x, I can differentiate with respect to x this equality. I get the derivative of sine y is the derivative of x, and y is a function of x. So on the left hand side I have sine of some function, so I'm going to differentiate that using the chain rule. I get the derivative of sine evaluated at y, and I have to multiply by the derivative of y. So I get cosine of y multiplied by derivative of y, which I will denote dy over dx. On the right hand side, I differentiate x with respect to x, I get 1. That means dy over dx, the derivative I'm looking for, is 1 over cosine y. Of course, I would like to have that as a function of x rather than as a function of y. So what can we do? Well, cosine square plus sine square of y is 1, and therefore cosine square y is just 1 minus sine square y. So I could rewrite things in terms of sine square y, and the reason why we do that is because, as you can see here, sine y is equal to x. So cosine square y is really 1 minus x squared. Now what I want is not cosine square y, it's just cosine y. But y here is between negative pi over 2 and pi over 2. And if I take cosine of an angle between negative pi over 2 and pi over 2, it's going to be a non-negative number. Therefore, if cosine square y is 1 minus x squared and cosine y is positive, then cosine y has to be the square root of 1 minus x squared. Right? If I didn't have this condition, I would have that cosine 1 is either the square root or the opposite of the square root. But since I know cosine 1 is positive, I know that cosine y is square root of 1 minus x squared. So I can plug it in here, and remember that y was arcsine of x. So what I have here is the derivative of arcsine of x is 1 over square root of 1 minus x squared, which we're going to write out this way. So we've established what the derivative of arcsine is. Now, as you can see, this makes sense as long as x is between negative 1 and 1 with the endpoints excluded. Arcsine is defined on the interval negative 1, 1, including the endpoints. And this is a situation that is consistent with what we have already seen on the graph of the function, because the sine function had horizontal tangent at pi over 2 and negative pi over 2. So in the reflection about y equal x, we got vertical tangents at negative 1 and at 1. So these vertical tangents here correspond to the limit of the function 1 over square root of 1 minus x squared when x approaches either negative 1 or 1. Okay, so this is what we have so far: the definition as inverse function, the derivative, the graph. Let's look at what it means in very concrete terms. Let's say, for instance, you want to calculate arcsine of 1/2. What does that mean? Well, according to the definition, arcsine of 1/2 is really the angle between negative pi over 2 and pi over 2, whose sine is equal to 1/2. Well, if you look at that, certainly the only angle between negative pi over 2 and pi over 2 whose sine is equal to 1/2 is pi over 6. Okay, now what if I plug an arcsine into a sine? So let's say arcsine of square root of 3 over 2, I plug that into a sine. Let's look at what do we have inside the parentheses. Arcsine of square root of 3 over 2 is the angle between negative pi over 2 and pi over 2 whose sine is square root of 3 over 2. Well, certainly if it's an angle whose sine is square root of 3 over 2, if I plug it in a sine, I get square root of 3 over 2. Of course, in general, just because sine and arcsine, well, at least a restriction of sine to negative pi over 2, pi over 2, and arcsine are inverse of each other, so when I compose them, I get the identity function. So for any x in the domain of arcsine, if I plug arcsine x in sine, I get x. And because they're inverse of each other, similarly, if I plug sine x into arcsine x, I get x as well, but with the caveat that x has to be an angle between negative pi over 2 and pi over 2, because they're inverse of each other if you take the restriction of sine to negative pi over 2, pi over 2. Now what does that mean? That means that, for instance, if I plug sine pi over 4 into arcsine, I get pi over 4. But if I plug sine, say, 2 pi over 3 into arcsine, I have to be a little more careful, because we have this condition that things work out if the angle is between negative pi over 2 and pi over 2. And here 2 pi over 3 is not, as you can see from this picture, 2 pi over 3 is not in this blue zone that corresponds to negative pi over 2 pi over 2. So what do we do in this case? Well, I'm plugging a sine into an arcsine, and I would get the identity as long as the angle is between negative pi over 2 and pi over 2. So all I need is to find another angle that is between negative pi over 2 and pi over 2 and has the same sine. And this is easy to do. Here is the angle pi over 3 that obviously has the same sine, because if I take the intersection of this half rays with the trigonometric circle, the projection on the y-axis is the sine of the angle. So in that case, sine of pi over 3 is the same as sine of 2 pi over 3, and pi over 3 satisfies the condition that it's between negative pi over 2 and pi over 2. So we can replace sine of 2 pi over 3 by sine of pi over 3, and now we can apply this formula and obtain pi over 3. Now to conclude, what if I want to calculate these kind of things, like arcsine of 1/3, it is some angle between negative pi over 2 and pi over 2, and I want to plug it inside, for instance, tangent function. I could pick another trig function. How do I calculate that? Well, as I said, arcsine of 1/3 is just an angle, and we know a few things about this angle. One, it's going to be greater than 0 and less than pi over 2. Because it's in the range of arcsine, it's certainly between negative pi over 2 and pi over 2. It is greater than 0 because if it was smaller or equal to 0, then the sine of that angle would be smaller or equal to 0, but the sine is 1/3. This is the second thing we know. The sine of that angle is 1/3. Of course, it's not pi over 2 because otherwise the sine would be 1. So sine of theta is 1/3 and theta is between 0 and pi over 2. We can interpret that graphically as the ratio of the opposite side to the hypotenuse in a right triangle is 1 to 3. The tangent of that angle is going to be 1 over L, where L is the third side in the triangle, in other words, the adjacent side to the angle theta. So all we need is the value of L, which is easy to obtain using the Pythagorean theorem. We have L squared plus 1 squared is 3 squared. In other words, L squared is 9 minus 1, 8. So L is square root of 8, which I can write 2 square root of 2, because 8 is 4 times 2. And therefore, the tangent of this angle is 1 over 2 square root of 2. Multiplying top and bottom by square root of 2 to rationalize, we get square root of 2 over 2 times 2, so square root of 2 over 4. But that's, since theta was arcsine of 1/3, this is exactly what we were looking for, the tangent of arcsine of 1/3. Now turn to the next video to look at other inverse trig functions.